So we will take the level of complexity and hardness for the diffusion convection problem from 1 dimension into 2 dimension. It's not really complicating the issue. It just requires more additional steps to do, because moving from 1 dimension to 2 dimension is going to add more cells around the central point. So instead of only dealing with east and west nodes, we will have the north and south nodes. And we dealt with that before when we covered the 2-dimension diffusion problems, but now we are looking into the 2-dimension diffusion convection problem. So again, starting from the general transport equation, we have partial rho phi by partial t plus nabla dot rho v phi equal nabla dot kappa nabla phi plus the source term, right? Again, we're still at that level. We are doing steady, so that's going to be 0 for a steady state. Since we are doing 2-dimension here, the velocity vector will have 2 components, which is u in the x and v in the y, and that's it. So the simplified equation here to meet that 2-dimension diffusion convection problem would be actually nabla dot rho v phi equal to nabla dot kappa nabla phi plus, depend if you have a source or you don't have a source, you keep that way. After you simplify the transport equation, you're going to integrate that over the control volume. That's the approach or the methodology in the finite volume method. Then you're going to use the divergence theorem to convert the integration over the control volume to the flux integration over the control surface. So I'm going to end up having control surface here, rho v phi dA, right? Equal to the integration over the control surface of kappa nabla phi dA plus the integration over the control volume of S phi. And we know that this could be transformed into either an average value, volumetric value times delta V, or could be expressed as SU plus SP times phi, depending on how the source is defined in the problem. Then this will be simplified by summation over the control surface for rho v phi dot A, right? Which end up to be F east phi east minus F west phi west. And this is what we used to do when we have a 1-dimension diffusion problem. Now, if I draw my domain, I will have, this is my P point. I will have east cell, I will have west cell, but now I'm going to add north cell and south cell. So I can connect these points here. Now, if this is a central point, so my domain faces are here. So this is now the east face, west face, north face, and the south face. And these are all small letters, right? So now this is not going to stop. Again, this is the U component. This is the V component. So I'm going somewhere into that velocity vector in this way. Again, this is a positive way of the U, and going up is a positive way of V. We talked about having negative, right? If that's U in negative, U in negative, and V in negative is going downward. So again, we're going to start assuming everything is positive. That's a standard case. And in this case, I'm going to add to this plus the F at the north, phi at the north, north face minus F of the south, phi of the south. Why the west and south are negative? Because the unit vector pointing outward in, if you guys recall that, in, and the flow is in the same way. So the angle is 0, cosine 0 is 1. That's why it's positive. But the angle between n and the velocity going up here is 180, and that's give us the negative value. So that's the approximation of the diffusion term for the 2-dimension convection part. If you want to approximate the diffusion term, that's convection term. Approximating the diffusion term is going to be summation over the faces for kappa d phi by dx, so it's going to be simply kappa. So that's actually kappa nebula phi, which is going to be dot dA or dot A actually. This will be kappa east A east d phi by dx on the east face minus kappa west A west d phi by dx on the west face. Now I'm going to the second dimension. I will have plus kappa north A north d phi by dy on the north face minus kappa west kappa south A south d phi by dy on the south face. Again, we have to approximate the temperature gradient or the phi gradient, and we're going to approximate the value of phi on the faces as well. So, and that's what we used to do in the previous lectures. So if I substitute this into the main equation, the general equation will become as follows. I will have f east by east minus f west phi west plus f north phi north minus f south phi south equal to kappa east A east d phi by dx on the east face minus kappa west A west d phi by dx on the west face plus kappa north A north d phi by dy to the north face minus kappa south A south d phi by dy on the south face. This is now the equation. For the diffusion terms, for diffusions, we always use the central differencing scheme, which means that d phi, let me draw again here, that's the cell phase boundaries. There's one node, there's one node, there's one node. That's the P, that's the east, and that's the west. So we usually have, this is the east face here, and this is the west face, right? So d phi by dx on the east face is always approximated by the linear variation, right? So it's going to be phi east minus phi p divided by the distance in between, which is delta x east. D phi by dx on the west face will be phi p minus phi west divided by delta x west. Now we need to go to the north and the south nodes to add the second dimension. North node, south node. So I will have d phi by dy to the north face, which is this face here, can be approximated by phi north minus phi p divided by delta y north. And d phi by dy on the south face is phi p minus phi south divided by delta y south. This distance here, that's delta x east. Distance here is delta x west. The distance here is delta y north. And the distance here is delta y south. No surprises here. These are the diffusion terms, and we did that multiple times, but now we are adding the second dimension. For the F parameter, we know that F east is equal rho times U times A. And for the east face, the area are going to be that height here, which is delta Y times the depth, which is always 1. So this will be rho U delta Y dot 1. So I'm going to end up having rho U delta Y. And again, this is a mass flow rate crossing the east face. F west will be rho U times A as well. It's going to be rho U, even the, it's a west face, but we still have the height is the same, that's delta Y. So I'm going to have delta Y dot 1. So this end up to be rho U delta Y. Again, this is the mass flow rate crossing the west face, right? Do the same for the north. It's going to be rho the velocity component in the north direction is going to be v times the area, and the area for the north face, it will be delta x times the depth. So I will have rho u delta x dot 1, so this is going to be rho u delta x. Same for if south, would be rho v times a, which is going to be rho, this is v delta x dot 1, so this will be rho v delta x. And that's a beauty when you pick up delta x and delta y are the same. This is a delta x distance here. So it's going to simplify everything. And if you pick delta x and delta y are the same, and we always assume rho is the same, but you may end up having u and v are different. So be careful here when you calculate each one of these, because two of them are based on the v component and two of them are based on the u component, and they could be different in values. So in this case, we will not have all the if values are the same. So be careful. Now we'll go for the convection term. For the convection, what do we need to define? We need to define the phi east, phi west, phi north, phi south. So I need to get phi east, phi west, phi north, phi south. How we get that? We did multiple schemes to do that. You can use the central differencing. You can use the upwind differencing. You can use the hybrid differencing, or you can use the quick scheme. So these are the different schemes that we did cover in the convection side. So depend how you're gonna do, how you're going to, it's your choice to pick up the scheme. So for example, if I'm interested to go for the simplest, well, like central differencing, phi east, the phi on the east face will be simply phi e plus phi p divided by 2 if the distances are the same. Remember, I give you an equation that's showing the general form of that phi if the distances are not the same. So be careful and go back and check that equation in previous recording as well. Phi on the west face will be simply the average of phi west plus phi p divided by 2. If I want to go for the north, it will be phi n capital plus phi p divided by 2. Phi of the south face equal the average of the south node and phi p divided by 2. These are based on the central differencing scheme. Let's assume that we are dealing with upward scheme. For example, phi east will be phi p, phi west will be phi w, phi north will be phi p because the flow is going this way, and the flow is going this way. That's v, that's u. So phi east will be phi p, phi west will be phi w, phi north will be phi p, and phi south will be phi south. This is the face and this is the node. So that's how you do that if you are using the upwind differencing scheme. So it depends what schemes you are using, and it will give you the value that you're looking for. And we're going to practice an example using different convection scheme into that two-dimension problem so you can get practice for it. So let's stick to the central differencing scheme here and see if we substitute how the equation is going to look like. So if I do that and stick to the central differencing scheme, I should get the following here. I will get, again, the equation is f east, phi east, minus f west, phi west, plus f north, phi north, plus minus f south, phi south, equal to kappa east, a east, d phi by dx on the east, minus kappa west, a west, d phi by dx on the west, plus kappa north, a north, d phi by dy north, minus kappa south, a south, d phi by dy south. So if you substitute, I should get the following. I will have f east, and phi east will be simply phi e plus phi p. I should divide by 2. I will take the 2 outside here, minus f west over 2. I will have phi p minus phi west, plus f north over 2. I will have phi north minus phi p minus f south over 2, phi p minus phi south, and that should equal to kappa A over delta XE, kappa east, A east over delta X east. I will have phi E minus phi P, plus same for the west, but this time will be phi P minus phi west, plus, that's actually, yeah, that's plus. No, that's actually minus. Yeah, that's minus. It's already right there. Plus the kappa north, A north over delta X, delta Y north, phi N minus phi P, plus kappa minus kappa south, A south, delta Y south, phi P minus phi south. Then you collect the term, you will find yourself on the right-hand side having d east minus f east over 2 phi east, plus d west plus f west over 2 phi west. Then I will have d north minus f north over 2 phi north, plus d south plus f south over 2 phi south. On the left-hand side, I will have a big bracket with fe over 2 minus f west over 2 plus f north over 2 plus f south over 2 plus d east plus d west plus d north plus d south, all of that multiplied by phi p. So this is A east, A west, A north, A south. D east is here, is its values here, but it's missing fe over 2. I have fe over 2 positive, but I don't have the negative. So I'm gonna add plus fe over 2 and subtract fe over 2. Now I can take this and I call it A east, right? The same for the west. There is f west over 2, but it's negative here. I'm gonna add f west over 2 and minus f west over 2. You will take the positive term with d west, so you can call it A west. So you're gonna end up adding a half of f east or f west or f north or f south. You will end up having d east plus minus f east over 2 plus d west plus f west over 2 plus d north plus, that's gonna be minus f north over 2 plus d south plus f south over 2 plus you will have fe minus f west plus f north plus f minus f south. This is totally multiplied by phi p. On the right hand side, I will have A east, phi east plus A west, phi west plus A north, phi north plus A south, phi south. And again, this will be A east, A west, A north, A south. This is my minus SP, but I know that if I pick up all the F values are the same, this will end to be 0. If they are not the same, they cannot be canceled out. But mass flow rate in and out, right? It's gonna depend on the U and V actually. So you cannot tell that. So that's not gonna be 0 unless you have the U and V are the same. Otherwise, you're gonna get east and west values Actually, no, if they're gonna cancel out. Yeah, north and south, the velocity will be the same, so it will cancel out. So yeah, it's the key player here is delta x and delta y. If you pick delta x and delta y are the same, you end up actually canceling this term. So I can write this equation here, and this is what? This is my total AP. So the final equation or the generalized equation can be written as AP phi P equal A east phi east plus A west phi west plus A north phi north plus A south phi south. And this is a general equation here. Then you have to define each one of the terms. So we know that A east is simply D minus F over 2. I assume that you're going to pick D and F are the same, right? So there's going to be D minus F over 2. A west will be D plus F over 2. A north will be D minus F over 2. A south will be D plus F over 2. And you can get actually your AP. It's going to be the summation of all these coefficients here. If you add up all the A's, it will end up to be actually 4D. Then it depends on SP. Mostly it's going to be 0. There is no source term in here. And that's conclude that part here. So now we can actually apply two-dimensional diffusion convection problem in a simple way. That's a straightforward thing here. It gets complicated when you add the source term, but at least we know now how to apply that. And we should practice an example to understand how this actually works. And that's what's going to be in the upcoming recording.